Can I get my exam back?
Yeah,
What's your lesson?
so I still have a bunch of unreturned exams, so if you're watching this lecture recording and you still don't have your exam back yet, pick it up from your recitation TA after break, because right after this class I'm going to split them up and hand them back to the TAs. Or I guess if you're like coming in late during this lecture, you can pick it up from me at the end of lecture. And then because we don't have class next week because it's Thanksgiving break, rather than having the regrade request deadline 1 week after we hand back the exam on Wednesday, it'll be instead 2 weeks later, so the Wednesday after break. So a reminder for how to do that, just staple a sheet of paper on the front saying what you want looked at and why. Definitely might be worth your while to sort of check it against the key and see if there's anything you're missing, or run it by me or your TA ahead of time if you're not sure. Okay. So any questions about that? Okay, cool. So chapter 9 sapling is still open, and I haven't set the deadline yet because we haven't finished the chapter, but that'll definitely be due well after break. So we still have several reactions left from this chapter to cover. Okay, any questions about that? All right, cool. Alrighty, so we finished up the main part of this chapter, which is all the E1, E2, SN1, SN2 stuff, but we still have a few more reactions in this chapter that involve alkyl halides. So a few more alkyl halide reactions. Okay. So the first one we're going to cover is actually probably going to be the most useful moving forward. It pops up here for the first time, and then we don't see it for a while, and then like suddenly in OChem 2, it shows up in a whole bunch of places during the semester, because these are very useful reactions that you can do. Okay, so we're going to look at, for the first time, organometallics. Okay, so we've already seen a bunch of molecules that have an organic part and a metallic part. For instance, like tert butoxide has a metal in it. It's got that sodium counterion that drops off, leaving the butoxide part behind. But not all of them count as organometallics. Here, the defining characteristic is it has to have specifically a carbon-metal bond. So you get that C directly bonded onto the metal. So there's a ton of different types of metal, which means there's a ton of different types of organometallics potentially we could make. But the two that are sort of the most heavily used, and that we're going to see in this chapter first of all, are two kinds. Organolithiums, which I guess organolithium reagents more formally, which have a carbon-lithium bond, not surprisingly. And the other one is Grignard reagents. It's spelled Grignard, but it's pronounced Grignard, like that GN combo, like in lasagna. So Grignard reagents were created by Victor Grignard a while back, and their hallmark is a carbon-magnesium bond. Okay, so if you've used the exam archives for studying for our third exam, you probably saw a couple of these pop up already because in previous semesters without snow days, we had actually covered it already by exam 3, but we're just getting to it right now. So we're going to dig into these a lot more today. Okay, so kind of an important factor here is most of the stuff we've seen bonded to carbons so far in this class is either about the same electronegativity, so like other carbons or hydrogens, or is more electronegative than carbon, so like oxygen, maybe nitrogen or halogens. These are really weird and different because metals are all going to be, or at least like these two, lithium and magnesium, are a lot less electronegative than carbon. Which means we're in sort of a weird situation. So here's an example Grignard. So note that one slight difference between them, if you look at a periodic table, lithium's in the first column of the periodic table. So it takes +1 charge, while magnesium takes a +2. It's in the next column. So magnesium actually needs another halogen on there to sort of balance it out charge-wise. Okay, so this carbon-magnesium bond is actually polarized towards the carbon, weirdly enough, kind of the opposite of what we're used to seeing. So we can show it this way, or we can do sort of what we've been doing with like alkoxides, like tert butoxide before, and actually show this bond breaking onto the carbon, giving it a lone pair and a negative charge, which means the MgBr is sort of left floating around as a counterion. If you want, you can actually split this up into like Br minus and Mg2 plus, but these two tend to stay together a little bit better than carbon does. Okay, so if we wanted to show the arrow pushing for this, it would just be we break the C magnesium bond, dump those electrons directly onto the C. Okay, so we can either show this as the covalent form, in other words, or we can show it as the ionic form. Realistically, like I know when we covered these two forms in chapter 1, we're like, these are what covalent bonds do, these are what ionic bonds do. Really, it's more of a continuum than like a black and white thing. So you can sort of think of like a covalent bond that gets more and more and more polarized in one direction until it's pretty much an ionic bond. Grignards and organolithiums are probably somewhere around the middle of that scale. Like it's about equally accurate or equally inaccurate to draw them as covalent or ionic forms. So really whichever way you show it is fine, just so long as the arrow pushing that you're drawing for whichever one you have makes sense. Okay, so for Grignards, we can break the bond towards carbon, give it a minus charge. For lithiums, we can do exactly the same thing. Here's an example organolithium. Note that the lithium doesn't need anything else on it because it just wants the +1 charge. So if we break that bond onto the carbon, we could show this as carbon with a negative charge, lithium with a positive charge. Okay, so they're more or less functionally equivalent as far as we're concerned for now. They're both probably around the midpoint of the, like, I guess, covalent to ionic kind of continuum. Okay, so questions about that so far? Yeah.
I might have missed this, but in the covalent form, are they actually covalently bonded, or would they dissociate in water?
So, is the answer to that. It's sort of, there's sharing of electrons, but it's really heavily tipped in one direction. And so I guess to answer your question, would they dissociate in water? It turns out to be completely irrelevant because they do something else very, very enthusiastically in water instead, which we're about to cover. Yep. Okay, so that actually leads me into the next part of what I'm about to cover, which is, so about half-ish of the time, or like half of the characteristic of this molecule, you can show it as carbon with a negative charge, right? So you don't have to know actual pKa values, but if you remember seeing like alkanes on the pKa table on your exam, about how strong would this be as a base with a negative charge on there? Like real strong, right? That's actually like the strongest bases that we're ever going to see in this course. So these things, carbon with a negative charge, when we saw carbon with a positive charge, which we've done a bunch of, we called it a carbocation. This, carbon with a negative charge, is called a carbanion. I don't know why one of them gets an O in the middle and one doesn't. I guess it's because anion starts with a vowel. But anyway, so carbanion with a negative charge is a very strong base. Depending on what the rest of the molecule looks like, you know, there's other factors that can sort of scale its pKa up and down. If you remember, like the orbital effect, maybe if this carbon is triple bonded to something versus double versus single, that'll scale it up and down. But usually, for just alkanes, usually the pKa is going to be somewhere around 60-ish. it can come down to like 45 if it's double bonded or so, and maybe like mid-20s if it's triple bonded, but it's still stronger than most of the other stuff that we're going to see. Okay, so what this means is that if we do try to put this thing in water, acid-base reactions are very favorable. So, and you can show this in either the covalent form or the ionic form. I'll draw it both ways just so you can see what that looks like. So if we show this in the covalent form, even though we're not explicitly drawing it as a carbanion, we can still say, okay, here's a water molecule or an alcohol molecule or something, anything protic basically. This bond you could go use to rip a proton off of pretty much anything remotely deprotonatable and get a new H bond here. And meanwhile, the MgBr plus is dropped off on its own, and the OH minus is dropped off on its own. Note that in this case, we're actually creating just a molecule of propane, which is going to bubble up out of the reaction as a gas. And because of the large amount of energy liberated when you do this reaction, because of how favorable it is, this will often just catch fire on its own. So Grignards plus water, if you have a lot of water, is kind of a dangerous setup. It's very easy for these things to get run away, like pretty quickly if you react them with anything protic. Or if you just have like a trace amount of water on your glassware, this Grignard reagent is not long for this world because it's immediately just going to take a proton off of whatever it can. Okay. So you can show this in the covalent form, or you can show just as well in the ionic form, which may make a little bit more sense just in terms of like how we're used to showing acid-base reactions. But really it's exactly the same thing. The only difference is, if we're showing it covalently, then when the attack happens, it comes out of the carbon-metal bond. Or if we're showing it ionically, the attack comes out of the lone pair that we dumped onto carbon. Okay, so questions about that so far? Yeah.
If we show it in the ionic form, do we have to include the magnesium?
Yes, just because, like, I know we've been pretty lax about showing that before when we were doing it with like terbutoxide or whatever. It turns out that a lot of the time the counterion on like alkoxides doesn't really matter that much, like it'll come off pretty easily either way. Here, because you're leaving a much stronger base, like it does actually make some difference how strongly bonded on there it is. So yeah, usually you would want to show the counterion for these all the time. Okay. So I guess, how do we actually make these things? So this is why these reactions show up in this chapter that's all about alkyl halides, because we can make them straight from alkyl halides. Okay, so we're going to start with the alkyl halide that we want to use, plus whatever the neutral version of the metal is. So either solid magnesium or solid lithium metal. And it turns out the solvent for this, like we've been pretty lax about solvents in the past too, because a lot of the time they don't really affect the outcome. In this case, the correct solvent choice is very important. It turns out you pretty much have to have some kind of ether solvent most of the time. So usually THF or diethyl ether is kind of the default choice. It turns out that these are actually doing something to help stabilize the Grignard, like they're all sort of If you guys remember that like solvent caging effect stuff that we saw in high dielectric solvents where they're all stabilizing a carbocation, they're sort of doing the opposite here where they're all helping to stabilize the carbanion by having sort of their polar parts of the molecule around it. And also they're aprotic, which means that they're not going to just do this proton transfer stuff right off the bat. So THF or diethyl ether, by far the best solvents for dealing with these organometallics. It turns out for organolithiums, so here's one slight difference between them. Organolithiums, you can actually get away with like hexanes or like some sort of alkane solvent. But it's not as good or easy to work with as THF. Usually THF is kind of the best solvent for these reactions. And in OChem 2, when we actually have you start using these for carbonyl chemistry, THF is the solvent that we have people use in that experiment. Okay. So the actual setup for this reaction is pretty simple. If you start out with some sort of alkyl halide here, maybe a chlorine on there, and you hit it with Mg and THF, you might occasionally see the Mg either written as Mg solid or S, or Mg with a 0 charge in parentheses, just to make it clear that we're not adding some sort of magnesium ion. It's like the straight up neutral magnesium metal. Okay, the mechanism for this is kind of weird and complicated. It involves sort of a single electron transfer getting wedged into like the anti-bonding orbital here, and then like later on the other electron gets dumped in there too. So we're not going to cover that, but basically think of it as this magnesium just sort of like wedges itself right into the middle of the carbon-chlorine bond. So like that. Okay, so that's how you do it with magnesium. Lithium is almost the same. Again, you start with an alkyl halide that corresponds to what you want to make, and you use lithium 0, and let's go with THF again because I like it. So lithium here. The difference is that we already know that you can't have like the lithium still attached to the halogen. So here it's sort of like 2 lithium metal atoms are wedging themselves into the middle of this carbon-chlorine bond. So you end up with 1 attached to the carbon and 1 attached to the chlorine. So again, that's because lithium can take a +1 charge and magnesium can take a +2. So you sort of need 2 copies of lithium to finish this reaction up. So if you want, you can actually say 2 lithium atoms on the arrow, but given that anything written on the arrow is always assumed to be present in excess unless we say otherwise, you don't even have to bother writing that. Just say lithium on the arrow and it's assumed to be enough to do whatever you need. Okay, so questions about that? Okay, cool. So this is actually kind of useful. Well, extremely useful in the future. Right now, we're only going to see it used for a few things that are of moderate usefulness, I guess. So one thing we can do with these, based on the chemistry we've covered so far, is we can now turn alkyl halides back to alkanes. I guess I shouldn't say back because we haven't covered how to turn the other direction yet, but we will in a second. Okay, so turn alkyl halides to alkanes in 2 steps. So if we take and say this alkyl halide here, and we hit it first with magnesium and THF, then we're going to get the Grignard on there. And now if we take that and react it with water, we already know that this is just going to do what's called quenching the Grignard and stick a proton on where the metal was a moment before. Okay. So this is the very first example we've seen of stringing two reactions together, one right after another. We're going to talk about this more at the end of this chapter, but we now have a way to take an alkyl halide, turn it into something, and then turn that something into something else. Okay, so this is maybe useful if you've got a halogen on there and you want to get rid of it. One other thing it is actually super useful for is pretty much the same reaction, only instead of using water, let's use fancy deuterium labeled water, D2O. So if you remember, deuterium is an isotope of hydrogen. But we can actually, like, it behaves differently in an NMR, for example, so we can actually, like, learn some things chemically about the structure of whatever we're working with if we can get a deuterium stuck on at a specific location. So D2O instead of H2O. Or if we're feeling really spendy, we could use tritium, which would be T2O. Again, another isotope of hydrogen, this one with, instead of just a proton like for hydrogen, or a proton plus a neutron like for deuterium, tritium has a proton and 2 neutrons, which is why it has a weight of 3, which is why it's called tritium. Okay, so we could do something like magnesium THF, bromine there, and then D2O lets us stick on a deuterium in a particular location. Okay, so we're going to do a whole lot more with these molecules like in the future, but for now we're just sort of like, here's how you make them, here's how you immediately destroy them by reacting them with something protic or deuterated. The end for now. Okay, questions? Mm-hmm. Oops, yes it is. Thanks, good catch. Okay. Other questions about that? Okay, cool. So that's one type of organometallic that we're going to sort of start out with. All right, so now we're going to switch gears and look at a different thing you can do in this chapter. Okay, so right at the start of this chapter, we mentioned that the eliminations that we're seeing, like E1 and E2, are both beta eliminations. But it turns out we're actually going to see a little bit from something somewhat related but different, which is alpha eliminations. So to do this, we're going to need something called carbenes and carbenoids, which are basically things that are close to carbenes but not really. Okay. So, unlike beta eliminations, where you lose a beta hydrogen and then the halogen off of the alpha carbon. All right, so that's the general idea of what's happening in both E1 and E2. Remember, we're losing the H off of here. We can, if we set it up right, we can do an alpha elimination where we're losing an H and an X off of the same carbon. But then the question is, like, what the heck does that look like afterwards? Like, we can't make a double bond between the two carbons that each lost something because there's only one carbon and we can't double bond it to itself. So how is that actually going to work out? All right, so let's look at how this actually might happen in practice. So it turns out that if you have this molecule, it's drawn differently from how we saw it in Chapter 8, but does anyone remember what this one's called? Almost. It's only got 3 chlorines, though. Yeah. Chloroform, yep. So this is actually almost the same solvent you use for running NMR, only instead of CdCl3, it's CHCl3, just regular chloroform. Okay, so if we take this molecule and we hit it with a strong, bulky base. All right, what base is that probably going to be? Terbutoxide, yep. Okay, so in other words, we want to discourage this thing from trying any SN2 funny business. We really want to just tip this towards elimination as much as we possibly can. So we're going to use a strong, bulky base like terbutoxide. This comes in and then deprotonates the carbon. Note that it can't do E2 because this carbon doesn't have anything else it could double bond to. So at least temporarily, it's going to deprotonate that carbon. You might be wondering, like, hold on, we know carbon with a negative charge is a very strong base. We just saw it over here. And the answer is, yeah, it is, but having the 3 chlorines attached to it really helps stabilize that negative charge because they're all pulling the charge out towards each other. So they're making that proton a lot easier to pull off than it would otherwise be. And also, you'll notice that all 3 of these things are leaving groups, which means they're also helping out because in the very next step, what's going to happen is one of them is actually going to leave right off that carbon, which puts us in a really weird situation because we know that the carbon here has a lone pair, but it only has 2 chlorines attached to it. So it's actually got an unfilled octet. So it's a carbon with no charge, but an unfilled octet. This is actually called a carbene. So you can almost think of it as a carbon that has a positive charge because we know it just lost some electron density and has an unfilled octet, and a carbon with a negative charge because of its lone pair at the same time. So those 2 charges cancel out, so it's not actually positive or negative, but it does still have very strongly nucleophilic behavior, like this lone pair really wants to go attack some stuff, and also very strongly electrophilic behavior, like this carbocation really needs some more electron density coming in from something else nucleophilic. So carbenes are really good nucleophiles and really good electrophiles. So very attacky and very attackable. Okay, so we can actually take advantage of these behaviors by introducing it to some other functional group that we've actually already seen in previous reactions that gets attacked by something at the same time that it's back attacking onto that same atom. Do you guys remember when we've seen that come up in the past? Yeah, halonium rings. So this is actually going to do the same looking step as forming a halonium ring. So if we bring in a alkene like this, and we have our carbene nearby, what's actually going to happen is this thing is going to attack the empty orbital on the carbon, sort of like attacking the bromine when it was making a halonium ring before. And at the same time, the lone pair is back attacking onto the alkene. So it's sort of getting attacked and attacking at the same time, which is something that we saw from bromine. Okay, so just like when we were making a bromonium ring before, we end up with both carbons of the alkene now attached to that carbon. One difference between this and bromonium ring formation, let me actually draw that up here for comparison. So remember when we did this with bromine before, we back attacked, but also to keep us under the octet rule, the other bromine had to drop off because this bromine, wow, that lone pair is way out there. This bromine already had a full octet, so it had to drop something when that happened. This carbene, though, already has like space for the incoming electrons. It doesn't have to drop anything. So when we looked at this product down here, the bromonium ring had a plus charge on that bromine due to kicking out a leaving group with a negative charge. That's not actually true up here, though. This carbon didn't have to drop anything. It's already kicked out a negative charge group in the past. And so we don't actually have a positive charge on here. So we don't actually have to do anything like to finish this reaction up. Like here, we would have to have something negative charged come in, attack one of the carbons, give the bromine its lone pair back. Here, we don't. We're done with the reaction. This is all stable and neutral now. So this is actually our final product. Just in one step, we make that three-membered ring, and that's it. We're done. Okay. So a few things to point out here. One is that even though we know that three-membered rings are kind of high energy and unstable, they're at least more stable than the carbene that we made in the first step up here, which means that this is a really, really useful way to access strained three-membered rings in ways that we couldn't normally do under other circumstances. So in other words, cyclopropane rings are kind of what we're aiming for here. So three-membered all-carbon rings, or cyclopropanes with potentially other stuff dangling off of it depending on what was on the alkene in the first place. But one other thing that's worth pointing out is these also, they're not just straight cyclopropane. They're cyclopropane with two halogens, two chlorine atoms, hanging off the one carbon you just added. Okay. So let me just erase the board here, and maybe I'll draw an extra example for this. Okay, so just realizing I don't have a picture of like how the overall reaction might look. Oh, yeah, I do. Here it is. Okay, so overall reaction, for example, might look something like we have an alkene here, and okay. So we have some alkene here. We hit it with HCCl3, which is our chloroform, and we hit it with some kind of tert butoxide containing thing. Maybe let's show a counterion just for completion, although it's not required. And then we go straight from the alkene to our new 2-chlorine having cyclopropane ring. Okay, so note here that we're actually drawing this as if the alkene is sort of our molecule that we care about, which a lot of the time it is. Like, even though we're sort of showing this starting out the mechanism with our chloroform molecule, it is sort of a smaller chunk that's just getting added onto whatever potentially large alkene that we're using as a starting material here. Okay, so questions about that? Yeah. Sort of, yeah. I guess like at least what's going on this particular carbon is alpha elimination, even if the actual like starting material like doesn't have any kind of elimination happening within it at any point. So, yeah. Okay. All right. Cool. So that's how to use carbines. They're fairly special purpose, but they are like one of the few ways to actually access these cyclopropane rings. But then the question is like, what if we don't want those chlorines on there? What if we want just a regular cyclopropane ring with no CLs? Okay. So, what we're going to do here is actually something fairly analogous to the organometallics we just covered. So, the name of this reaction is Simmons-Smith cyclopropanation. So we're making a cyclopropane ring using a method worked out by Simmons and Smith, I guess. Okay. So the way this one works is we're going to start out with something fairly similar to the actual carbene that we made over there. So instead of carbon with an H and 2 halogens, it's carbon with 2 H's and 2 halogens. Or sorry, carbon with an H and 3 halogens over there. Okay. So what we're going to do is hit this with a new type of metal, one that we haven't looked at making organometallics with. So this zinc Cu is often called zinc copper couple. And the copper part is a necessary catalyst to allow this to happen, but it doesn't actually get incorporated into the molecule at all. Zinc, though, acts like magnesium did in making a Grignard. So what we're going to do here is into one of the carbon halogen bonds, we're going to wedge in the zinc atom, just like we wedged magnesium into a carbon halogen bond before. It's only going to do it on one of the bonds for reasons that we'll look at in just a second here. Actually, let me scoot this out just a bit. Okay, so this bond, the carbon-zinc bond, is polarized so that carbon has more than its share of electron density. Meanwhile, the carbon-iodine bond is polarized the other direction so that iodine has more of its share of electron density. So this whole thing looks kind of like carbon has a delta negative because of the iodine, and at the same time it's also got a delta positive, it's got a delta negative because of the zinc, and it's got a delta positive because of the iodine. So this is something that's called a carbenoid. It's not quite the full-on, like it acts like it has a full plus charge and a full negative charge at the same time because of its lone pair and empty orbital. But it's sort of edging in that direction. It's got like some of a plus charge and some of a minus charge at the same time. And the reason we're specifically using zinc and iodine is because they just happen to put like pretty similar sized delta plus and delta minus charges onto that carbon. So it winds up like pretty neutrally charged overall. It's just acting kind of carbene-ish. Okay, so questions about that so far? Okay, cool. So again, if we bring this carbenoid around an alkene, it's going to do a pretty similar deal. So we can get this. The biggest difference is because we don't have like a really clear, obvious empty orbital or lone pair, when the attack and back attack happen, it's going to be a little bit more complicated. Instead of attacking from a lone pair on carbon, we're actually attacking from the carbon-metal bond, just like if we showed the covalent form of a Grignard going out and doing something. And instead of attacking an empty orbital on the carbene, like we did over there, we're attacking the delta plus on the carbon, which forces us to kick out the leaving group. So it is one more arrow, but you can sort of piece together like why each arrow happens the way it does compared to like the true carbene over there. Okay, so in this case, oops, that's going to get rid of our double bond, and both the zinc and the iodine are going to come off at the same time. Oops, leaving us just the carbon with the two H's cyclized onto there. Okay. So if we want to do the overall reaction, we could say some alkene again plus CH2I2, zinc and copper mixed together, and THF is just going to give us regular old cyclopropane with no halogens on it. Okay, any questions about that? All right, cool. So that wraps it up for those two topics. I guess have an amazing break, and I'm going to finish up the last part of Chapter 9 when we get back.